So today what I want to talk about is kind of our last lecture related to language, but now we're bringing the language domain and the image domain together. And the thing that makes it happen is a cool algorithm called CLIP, okay? And so, so far, all of our kind of image generation stuff has dealt with basically having a class of images that was known in advance. Just like what you did for your homework, you took a class of images like plants or Legos, you trained a GAN or whatever, and then you could make images of that thing, right? And then we talked a little bit about conditional GANs where you could specify a class, for example, like one of these ImageNet categories of cars or trucks or buildings or whatever. But what we want to be able to do is to make an image generation model like DALL-E 2 that can just take a natural language prompt as input and create the image, right? That's kind of, in some sense, what we've been building to all semester, and what we're going to talk about next time is this kind of like prompt-based image generation. For that, we need this critical glue that is called CLIP, okay? And so this is kind of like multimodal algorithm. So, how do kind of prompt-based image generation algorithms kind of process language. Right, so we talked about language generation models in the past couple lectures, but that's not exactly the same as what we need to make these prompt-based algorithms work, and the reason is that we need to make the connection between images and text, right? And so the key thing that made all this happen was a paper called CLIP, introduced in 2021 by Radke et al. Again, this stands for contrastive language image pre-training. And so even though this only occurred a couple of years ago, this immediately took off in terms of what is the kind of underlying glue that holds all these cool algorithms together. And now it's widely used as a method for relating language to images. So CLIP itself is not a generative model. You can't necessarily use CLIP to make language. It's not a model in itself, but it's designed to basically pick the description that best matches an image, or vice versa, right? So that's why it's kind of this key building block in generative models. And so CLIP was trained on a huge database. So trained on a data set of 400 million text-to-image pairs, which again were gathered in a variety of ways, like image captions of news stories and all sorts of public domain stuff. And there was also, I think, probably a huge army of image labelers out there that were given images and asked to describe them with a prompt, and then people rated how well the prompts worked and so on. Again, 400 million images is a lot, but actually that is now kind of small compared to current text image databases. So now, as a side note, there are an even larger databases. So a well-known one is called Lion 5B, and the 5B stands for 5 billion text-to-image pairs, right? And so these data sets are kind of actually interesting. I should put a link to the, I guess we can just take a look at it for a second here. So if we go to my webpage and we do Lion 5B, a new era of open, large-scale, multi-blah. Okay, so basically this came out in 2022, right? And so this is open in a sense, but it's a little bit also kind of weird. You don't actually get the text-image pairs directly. What you get are matching embeddings, right? So I think that to avoid issues with copyright and so on. Like they don't want to be responsible for hosting 5 billion images, which they may not necessarily own the copyright for. So instead, they will provide you with a database basically of, I believe, captions and then links to images. And then you can go follow the link yourself to find the image, and then you can use it, right? So it's a little bit of a murky area. It's interesting to read this. This is kind of like, you know, a more open access thing than the original CLIP database. So CLIP was originally OpenAI, and that was in ICML. But I don't think that the 400 million image to text pairs were available there directly either. So anyway, massive effort to curate these kinds of data sets. So here's the basic idea. And it's actually a super simple idea that works really well, right? So the idea is basically going to be to train 2 embeddings one of which is a text encoder, and one of which is an image encoder. Okay? And so if you imagine that you have a training pair, what you can do is you can say, okay, suppose I have a bunch of sentences, right? I put my sentences through the text encoder that I'm going to train. And then I produce, let's say I have 5 sentences. I produce 5 embeddings. So these are all like text embedding vectors. And then I could take the matching images and I could put these through an image encoder that I'm going to learn. And that produces 5 image embedding vectors. And it's important that these embeddings be the same dimension, right? So the embeddings have the same dimension. For example, a common number is 1024, okay? And now what I do is I say, okay, I want to train a model that will bring the image embedding and the text embedding of the corresponding pairs close together while forcing apart the ones that are not the same, right? So what I can do is I can more or less take the dot product of these embeddings, right? So I could take I1.T1, I1.T2, I1.T3, and so on. I can form these 25 by 25, I'm sorry, I can form this 5 by 5 grid, and I could say, I want these things down the diagonal to be close together, right? So say I'm going to, for example, maximize the cosine similarity between these vectors. So I have basically n positive pairs, and I have n squared minus n negative pairs. And I want to have the negative pairs to have low similarity and the positive pairs to have high similarity, right? And that's all it is, right? It's a very simple concept, except I do this with a database set of 400 million images, right? And so there's a question then about how do I do the embedding itself, right? So the authors experimented with a bunch of different architectures for both the text embedding and the image embedding, and ultimately they found that the best performance was with transformers, right? Like we talked about previously, transformers have kind of dominated the literature lately, and so it turns out that that's what they used for both of these different kinds of embeddings, right? So the text transformer is basically not that different than we talked about last time when we were talking about large language models generating text, right? We already kind of know how that works. The only thing is that instead of producing a softmax vector at the last step and then finding a word that you predict as the next word, instead I kind of keep that vector, and I'm not trying to do word prediction, I'm trying to stop at the last kind of layer of the network, right? So kind of similar to what we talked about for word prediction, except I basically stop before the softmax. So it's kind of like the highest level of transformer at the end of the text string. That's the output that I use. So the text part is pretty simple. And then on the image side, they use something called a vision transformer. Where, again, if you've done any sort of computer vision research, you know that the vision transformer is like a super common model for doing, computer vision these days. And the basic idea is to treat the image as a sequence of non-overlapping patches. And you can imagine that you kind of bring over this whole idea of positional encoding and so on, treating the image. So the idea would be like I take my image, I split it up into a bunch of non-overlapping patches. And of course, there are architectural choices to think about how big these patches should be and so on. I number the patches, blah, blah, blah. And then I can kind of think about just kind of like taking these patches and sorting them into a vector. And then now that I've got this kind of sequence of objects, this kind of sequence prediction thing becomes more or less like a sequence of tokens just like anything else, right? So the idea was that then I put this into some sort of a transformer encoder, which includes basically some sort of 2D positional embedding. Right? So that is, not only do I look at the sequence, but I'm more looking at the XY coordinate of the patch, right? Which I can encode. Again, you can imagine it kind of like an outer product of a cosine vector and a sine vector with different frequencies. So it's very similar to what we talked about before. It all sounds great in theory in terms of how to train these transformers, but in practice on the original data set, it took 12 or more days to train on 256 V100 GPUs, right? So it was a non-trivial effort to actually train this network to achieve the best loss, right? So, and then they basically released the result of the trained model that anyone can use. And so hopefully on homework 3, you're already using some implementation of CLIP that you found and didn't have to train for 12 days on some crazy computer, okay? So that's the basic idea. Let me pause and ask any questions or comments about this. Yeah? Say that again? Mm-hmm.
Right, so for CLIP, it's a text encoder, kind of like encoder only or encoder only structure.
Is a text, so I think that the encoder in CLIP is going to be, let's just look at the paper for a second. So since you see the prompt all at once, it doesn't have to be like a word prediction type transformer. It could be a decoder transformer like you were, or yeah, an encoder transformer, right? So where you see the whole thing at once. So if you look at the details of this, they go through all of the kind of model choices. And let me see if I can find the part about the text part. And actually, this is a very interesting paper to read, and I'll say a minute about it in a second. So here they have, this is the training part. So 5 resonets, 5 vision transformers, blah, blah, blah. I think they ended up using the vision transformer, which is why I didn't talk about the resonate part. I'm looking for the language part, though. This is the image encoder. '18, you say? If I can find it now. This page? Bottom left part. Am I in the wrong place? We're using different versions of the paper? OK. Yeah, I mean, they did a lot of experiments with the different structures of the 2 encoders. And now I can't put my finger on it. But the long story short is that there's no reason why you have to think about the prompt as a prediction problem. Basically, you look at the whole prompt all at once, right? That's definitely true. And so it's paying attention to the whole prompt, obviously. Yeah, that's a good point. Other questions? OK, so CLIP was super exciting because it enabled what's called zero-shot prediction on tasks it was never even trained to do, right? So, the cool thing is that suddenly people adopted CLIP to do all sorts of crazy things, right? So, for example, suppose that you wanted to do image classification, right? CLIP was not trained for that at all, right? So CLIP can do zero-shot prediction on, what I guess I would say, unseen tasks, right? For example, let's suppose we wanted to do classification. I could take my image and I could do my CLIP embedding of the image, and then I end up with a embedding vector I, okay? Now I could take a bunch of classes like, cat, dog, whatever. I turn each of these classes into a phrase, right? Like a photo of a cat, a photo of a dog, and so on. ... Each of these things I can now put into the CLIP text embedding, right? So these are the CLIP embeddings of these things. And then I can simply look at the dot product of each of these things and pick the one that has the highest similarity, right? And that gives me a classification, right? And so there's nothing that needs to be retrained or anything like that. I just use language as the common domain, right? And so definitely this type of thing is kind of like the early stages of what you would call prompt engineering, right? So, there are whole classes that will teach you about the right way to craft a prompt, right? And so a lot of times in these papers, you'll see that people are using a mixture of, a high resolution photo of X, a DSLR picture of X, right? And they'll use maybe 5 different descriptions of different ways of saying the same thing and do the CLIP embedding of all those text phrases, and then they will, use the average of the results to get the final answer, right? Now, one thing that was super interesting about CLIP, well, not super interesting, one thing that was super scary, I guess, about CLIP was the fact that it kind of, we talked about this last time a little bit, it bakes in all sorts of crazy implicit biases in the data set. So if you look at the original CLIP paper, they spend a significant amount of time talking about the bias issue, which I think is really good to know, right? So basically, I'm trying to find the part where it says here, right? So it says CLIP is trained on images from the internet, right? So there's going to be problems with the way that people describe images, and just in the same way we talked about last time, there's a huge amount of questions about fairness and bias and so on, right? Does it classify, white people different than black people, men different than women, right? So this is why, in a way, people would come up with these early examples of some of these generation models. They'd say, make me a doctor. It will make a picture of a white guy, right? You never get any black guys coming out of the prompt, right? And that's a kind of a baked-in algorithmic bias. And to their credit, they spend a lot of pages talking about the issues of bias, which I think is worth reading. So again, go back to the original paper and take a look. I think that's actually quite interesting. But certainly, there's definite issues with, what kinds of biases are baked in, and some of these things may be even subtle. If you're in a job that requires a official photograph, that photograph may be higher quality than just a selfie taken from a bad camera. And so then it's are you encoding kind of who could afford to have good photographs taken, and what do they look like? So the whole thing is, I think, very interesting. And also, again, it's the same kind of deal where you generate these models based on a huge amount of scraped data, but at that point, kind of the horse is out of the barn, and you have to figure out how can you mitigate the problems that you've created by not really thinking about the data set creation directly in the first place. I mean, with 400 million images, there's no way that you could be on top of all of the stuff that's inside your database, right? Okay, so CLIP came out, and obviously we'll talk about it next time in the context of just image generation for stuff like DALL-E. Certainly it's under the hood of all these kind of diffusion-based image generation models. But what I want to talk about today are a few of the CLIP-enabled things that tie back to what we talked about in the first part of class on other image generation. So CLIP, immediately made or immediately enabled many kind of cool natural language image manipulation algorithms. So maybe a good example to start with is, you remember this paper, GAN space, we talked about, right? So remember that GAN space, the idea there was that the authors took StyleGAN-2 and I believe also Big GAN, and basically they discovered by tweaking knobs in the latent space of the GAN interesting directions. Oh, if I turn this knob, it seems like the person becomes older. Or if I turn this knob, their hair color turns blonder, right? But they had to explore manually the space to give these text tags to what was happening in the image, right? So CLIP made it possible now to automatically find interesting edit directions and match them up with text without the human being in the loop at all, right? So GAN space basically required, human involvement to find interesting directions in latent space. So one algorithm that came out immediately was called StyleCLIP, which was by Polytechnic et al. In ICCV 21. And again, you're going to see, especially now and going forward, it seems like there are all these papers that are basically some combination of, StyleCLIP, GAN, NERF, all these things are just jammed together. So many papers to me all start to sound kind of like the same, because there's lots of style plus something or something plus CLIP. So let's just actually just revisit for a second, how does StyleGAN-2 work, because that was a while ago. So StyleGAN-2 refresher, the way that worked under the hood was that we had a latent variable z. We put that through a separate network to produce another kind of intermediate latent. W, and the hope was that this space was meant to be more disentangled than the raw latent space, right? So the idea was that the W space gave us more kind of sensical edit directions, right? So the way the W was used was that I put this W vector into a bunch of what are called affine, well, these are just affine transformations, kind of a bias and a scaling at every layer. And then what comes out of each of these was a style vector. And then these would go into different resolutions, right? So the top one would be 4x4, and the next one would be 8x8, blah, blah, blah. And then I would add some noise in here. You can go back and look at the StyleGAN lecture for refresher how this works. But basically, the idea was that there was this kind of key idea of this disentangled latent space W, right? It's possible that you could have a different W at every layer. So if W, whoops, wrong pen. So if W is different at every layer, this was called the W plus space. Right, you remember one of the things that you could do was you could kind of choose to mix the W vectors from different, you take image 1, image 2, you get their style vectors, then you kind of say, I'm going to take half the style vectors from this person, half the style vectors from this person, and make a mess, or make a mixture, right? So I could kind of make a choice about what I'm sending through to these things. And then also, after I go through the affine transformation, then this would be like what are called style space vectors, right? So, after the A block, these are called style vectors. So style space, we could call S, right? So the idea behind this Polytechnic paper was to do some searching through this W plus space, like the generalized W space, and also the S space, to be able to discover interesting edit directions, okay? And so the idea was to say, okay, let's suppose that I want to give a text directive, like I want to give this person a mohawk, or I want to give them red hair, right? So what I do is I have a kind of like text vector, or a text directive, right? So let me just write it this way. So there were a bunch of things proposed in this paper. One was, given a source image latent code, let's call it WS, in this generalized W plus space, and a text directive T. And this text directive is just like a natural language, right? Man with red hair, for example. Then what I do is I solve this problem. What I want to do is I want to find another vector in the W space such that I look at the distance between the CLIP vectors of the generated image that I get if I put in W and the text things, right? So this is, again, like an image from the StyleGAN generator. And then what I'm doing is I'm basically putting this into the CLIP image embed. And then I'm also putting this into a CLIP image embed. And I'm looking at the cosine distance between these two vectors, right? So again, this is the whole value of CLIP, is being able to directly compare an image and a text, right? And then I have an extra part that says I want to make sure that I don't stray too far from my original example. Oop, almost lost my microphone there. So basically the idea is to say, I want to start with this person as a prompt, right? So I want to make sure I don't go too far away from that latent, but I also want to make the text description of the image agree as much as possible with my modification, right? And of course, there are a couple extra things, like if I'm doing something specifically with faces, there's another optional term that says to preserve the facial identity as much as possible. And so that's simple idea, right? I just kind of solve this optimization problem over here in latent space. And then for real input images, the question is, like, where does the latent come from? So for real images, the first thing I have to do is to project them into the StyleGAN-2 to find the closest latent vector. And luckily, there are algorithms for doing that, right? So one algorithm is called E4E by Tove et al. Is one place, but there are other ways you can do it, right? And so the authors of this paper provided a nice online demo here. So here's an example of, picture of Taylor Swift, and the directive is a face with a bowl cut, right? And then it produces this thing. And I believe, let's see if we can do this live. Let's see, take a picture with my webcam. Integrated camera. Oh, I can't see what I'm looking at. All right, so I'm gonna come close to the camera. This is not great lighting. Oops, that didn't work. All right, take a picture. I don't want the bowl cut, so I'm gonna say a face. Let's see, a face with a beard. Let's start out easy. It looks okay. It's kind of interesting that it's kind of like, abstracted out the background and given me a beard, right? A face with red hair, let's say. No, not bad. And so actually you can see that there's definitely some differences in how it's taken my face and embedded it into latent space and then changed that thing, right? Do I have any other questions from the audience? A face with glasses, how about that? So this is all basically like being, that's not bad, basically being discovered on the fly. How about like an old man with glasses? Well, okay. Yeah. Can a cartoon face? We're going to talk about that in a second, but let's say this: a cartoon man or face. Let's see. There is something else I'm going to show you next that can do that. I think this is more for photorealistic editing. Oh, didn't like that at all, actually. How about like an animated face? No, didn't like that. So here are some other examples from the paper. So the top row are the real images, which then have to get embedded into the corresponding StyleGAN space, and then the bottom rows are the edits that come from just like giving it the text directive, right? Not sure why this is like a little bit cut off here. Oh, I know why this thing is like over here. Come back. Here. Yeah, so this looks pretty well. Let me just make sure, is there more I want to say about StyleCLIP? Right, and so here's, again, clearly like a Game of Thrones era thing, right? So taking these people on the left, I guess the guy in the middle is not a Game of Thrones character. I'm not sure who that guy is. And then giving them different, attributes, right? And so one of the things that this paper also addressed was that this optimization problem, could take a while to solve, right? And clearly it's being solved very quickly on the back end of this website, right? So another thing that you could do was, so this is slow because I'm doing it kind of on a image by image basis, right? I'm finding just for that image the best direction, and that's good, but it could take a while, right? So it would be better to find, I could also find a mapping in this W plus space for a given t that should apply to any input image. So it's not input image specific. Then what I would do is something like this. I would say I want to minimize the clip difference between the generated image, take the W, plus this MT of W, where this here is some sort of a trained neural network that tries to map T to a vector in latent space. And then I want to make this image match up with the text prompt. And then I want to minimize the amount of change I'm making in the space, right? So it's like saying, I want to learn a neural network. This here is going to be like a network that I learn that takes W in, or I'm sorry, it's a network for direction T. And so if you have these common directions like curly hair and so on, I could learn this and I could apply it to any image, right? Or they also kind of talked about this in style space instead of in W space, right? So the third thing that they talked about was, or I could find a single global direction in style space, this S space corresponding to T. And so the idea would be to say, I have a kind of a delta T, which is the difference in clip text embeddings of the direction I want and the kind of default, right? So I could say, it's like saying I embed the difference between a fuzzy cat and just a regular cat. Okay. And then what I want to do is we want a direction delta S in style space so that if in my generator I take the original image and I turn it into moving in the direction of delta S, and I embed, again using CLIP, this is my embedding vector here, and this is my embedding vector here. Kind of what I want is that this direction and this direction should be collinear in the same direction. And so basically what I want to do is I want to find a good direction delta S such that these two things are lined up in embedding space. And so the basic idea is that I kind of keep on trying different channels of style space to see if moving in that direction has a positive correlation with delta I, right? So I kind of am trying to kind of pick directions in delta S, or pick directions in S space that make this thing line up as well as possible. And then they discuss a lot of issues with respect to how all these things are entangled, right? Because we talked about that before with GAN editing, is that you change one thing and other things change, right? So they've spent some time talking about those issues. So in terms of cartoonification, which is what you asked about earlier, so there was another paper that came out just afterwards at SIGGRAPH called StyleGAN-NADA. And so the next paper I want to talk about is StyleGAN-NADA. And the NADA stands for, if I understand correctly, non-adversarial domain adaptation. This paper was by Gal et al. In SIGGRAPH 2022, so just last year. And so the idea would be to, what domain adaptation means is I want to turn a person into like a, Pixar cartoon, or into, I don't know, Rick and Morty, or zombie or something like that. So again, you've seen this kind of thing in apps and image filters and so on, right? And this is kind of like the underlying thing behind that, right? And so the kind of cool thing is that to do this, you don't need to have any kind of like before and after examples of your transformation, right? So I don't have to have an example that an artist has made of me as a Pixar cartoon. Instead, I have a bunch of examples of me and a bunch of examples of Pixar cartoons, and I basically turn me into the cartoon without having ever trained on that problem, right? And so, don't need to have, matched images from the target data set. Everything is done via CLIP. So how does that work, right? So the idea is we're going to have two generators. And so these generators could be just like starting with StyleGAN 2. So obviously, because it's called StyleGAN, right? So we have two image generators. One is called G-frozen. And this is pre-trained on a single domain. So for example, like faces. Okay? And this could just be like StyleGAN 2 trained on faces, right? And then I have a network that I'm going to train called gtrain that is initialized as gfrozen. And then I'm going to fine tune it to be fine tuned so that for any latent code W, it differs from gfrozen only in the desired direction, which is the text description that I give it. So again, how does this work? the idea is very similar, where I say, okay, I basically take the text difference between my two images, or between my two descriptions. It's like saying, my delta t is the same. It's like the embedding of the text of where I want to go minus the embedding of the text where I started. So it's just like the difference in CLIP text embeddings. And again, this would be like, a cartoon character of a man. This would be like a man, right? And then I have my delta I, which is like the difference in CLIP embeddings of the trained network when I put the latent in, and the frozen network when I put the latent in. And I want to basically minimize the cosine difference between delta t and delta I. Same thing. I want to be bringing those two vectors as close together as possible. And so again, the examples of this are also kind of fun, right? So this is what enables some of this kind of like Pixarification of photographs, right? Or you could have something that turns your dog into your Nicolas Cage dog, right? And so again, this is pretty cool. There's an online demo of it over here. So this is also linked to from the page. It is a little bit slow, so I did an example in my office before I came here. So again, here's a picture I just took a few minutes ago. At the upper left, you can see the embedding into the StyleGAN space, and then you can see all of the types of things that it's made. You got the Joker. Some of these I think are more successful than others, right? So like the anime cartoon, the Mona Lisa, sketchy version, zombie version, Super Saiyan version, Zuckerberg version, right? So you can play around with this. I didn't do this live because the website has this kind of like cold start where it takes like 5 minutes or so to kind of like spin up and get going. Once it's going, I think you can generate images pretty fast. So I encourage you to go and play with this. This is actually a site that I hadn't seen before called Replicate that makes this running super easy. And so it's kind of cool to check out. So again, that's linked to here from this StyleGAN-NADA demo page. OK, let's see if there's anything else I want to say about that algorithm before I move off of it. OK, so so one more thing that I thought was really cool was that here, so far, all of the users, so far all the text stuff is coming from the user, right? Saying, make this image look like this, right? And so there was a paper called CLIP to StyleGAN. This was by Abdal et al., also from SIGGRAPH last year. And so the cool thing about this was that they extracted the edit directions in an entirely unsupervised way. So this was basically extracting text labels of edit directions automatically. So in some sense, this is kind of like auto GAN space, right? So in GAN space, the authors poked around and found interesting edit directions and gave them names, right? Now the idea is that since we can use CLIP to find text strings that are matching up with image edits, we can actually find the names of the edits automatically and find interesting edits, right? So the idea here is basically to find interesting CLIP directions. And so here's the kind of setup. And again, you have to read the paper for all the details. But kind of the idea is that, what I should be able to do is, for a set of kind of similar input images, for example, again, coming back to like just like StyleGAN faces, the idea is that let's take those images, find their CLIP image embeddings, and then average them, right? And the idea is that if I average all these embeddings, it should kind of come close to the most neutral description of the class, or the most general description of the class, right? So if I took a bunch of StyleGAN-generated pictures of, men, then the average of that should have high similarity with the CLIP embedding of the text phrase "a man," right? So to write that down more specifically, the mean mu of the CLIP embeddings should be similar to the CLIP embedding of the phrase "a picture of X," where X is like the generic description of all the stuff you put in, right? And then what we're going to do is we're going to basically explore directions away from mu in embedding space, right, to find interesting directions that correspond with things that change the images, right? So the idea is to look for directions like mu plus moving in some direction v, right? And so the easiest thing I can imagine doing, and it kind of comes back to GAN space a little bit, is to look for PCA dimensions in the CLIP space, right? Those are probably interesting ways that I could move that come from my training data, right? So the idea here is that what I do is I have a, for a candidate direction vector v, I'm going to try to find a set of words to describe it. So first I'm going to kind of like find a bunch of relevant samples, right? So I've chosen a direction as a possibility, and now what I'm going to do is I'm going to say, okay, which of my images in my data set kind of like match up with that vector, right? So what I can do is I can say I'm going to look at the CLIP embedding of each of my images, subtract off the mean, and then ask which are positively correlated with the vector. And then I can look at basically like the dot product between v and this difference, and I can say, let's look at the stuff that is most correlated and least correlated, right? So basically, I sample the top 100, top and bottom image embeddings. This is like positive and negative examples, basically. And then that kind of gives me some sense of like, if there's something interesting there, I'm refining my choice of v to be more aligned with something interesting happening in image space, right? So I basically refine v plus as the average of these vectors. Right, so the idea is that, I'm kind of taking an idea and I'm kind of trying to find something where there's a bunch of images that kind of like positively correlate with that idea, and I'm only taking those examples, right? And now what I want to do is find a set of words such that this v plus direction in CLIP space is well aligned with a phrase like a picture of a person with blank, right? So the idea is to find a set of words so that the CLIP embedding of a picture of a person with blank, for example, say we're dealing with people, is aligned with this image, with this clip direction here, right? So there are a lot of steps to make this work, right? So kind of searching in word space is a little bit complicated, right? So there are lots of details to make this work. You know, there are a bunch of issues, right? Like, you know, you have to deal with synonyms, you have to just deal with disentanglement. So, you know, for example, like a picture of a person with facial hair and a picture of a person with a beard are kind of like the same concept, right? So you kind of want to make sure that these things are kind of like all taken care of at the time that you're learning, right? And then once you have the text labels, then everything else is kind of like more or less the same as like how you manipulate things in StyleGAN, right? So once we have the text labels, then we can find the corresponding like StyleGAN like W plus directions that match up with those things. So kind of similar to StyleCLIP, right? So kind of the idea is that we are poking around the data to find interesting ways that things vary, right? So we're trying to find interesting variations in our training set and give them names, right? And the kind of cool thing about this paper was that it could discover things that you might not have thought about as interesting combinations, right? So for example, you know, here is an example of the kinds of things that were discovered, right? So like words that we might know, like smile and kid and beard and hair, right? So this is all stuff that kind of could be done before with, you know, the human giving the name of the edit direction, except in this case, all of these labels are discovered automatically by the algorithm, right? And then something that was really cool was it came out with transformations that you wouldn't have necessarily thought about, right? For example, one thing I discovered was going from a car to scrap or vice versa, right? And that's something that, you know, if you trained on a StyleGAN database of cars, you might not have thought to use the word scrap as a edit direction, but this was found by associating that and finding that scrap in clip space matched up with this change in images, right? And in the same way, it discovers like red as a transformation that was not kind of, you know, automatically pre-programmed, and it can move in StyleGAN space to turn things to be red, right? So that was pretty cool. And so this is all enabled by kind of using this underlying layer of language as the common space. It wouldn't work if I couldn't embed an image and a text vector into the same space and look at their similarity, right? And so now you can kind of foresee how this is going to work for something like DALL-E, where we want to have a text prompt match up with the image as well as possible, right? And so let me just say on the piece of paper that, you know, the cool thing was, you know, can find kind of like unexpected labels. So in a way, it's kind of like exploring your data set automatically, right? And then there are a few other kind of like clip-enabled things that, you know, came out. So one kind of neat idea, which I've debated, you know, saving until another lecture, but there's something called clip draw, which was basically, again, last year in NeurIPS. So again, if we're thinking about revisiting old algorithms in the spirit of CLIP, right? So this is kind of like another shot at the old, like the Hertzman algorithm of painting strokes on a canvas. Now you can imagine doing the same thing. You could kind of like optimize stroke placement incrementally until the clip description of your image matches up with some text, right? And so here's an example of clip draw, right? So you can incrementally draw strokes of different colors, sizes, opacities, and so on. The top is basically trying to make an image that aligns with the phrase at Eiffel Tower, right? And the bottom is just like the ultimate result of giving a text prompt and having it draw strokes until the picture is lining up with the text prompt as well as possible. And so again, these are kind of like, you know, fun, not entirely obviously photorealistic, but you can definitely see these things coming out of it, right? Like I think that the horse eating a cupcake is pretty good. This kind of concept of self, is like this kind of like abstract cubist thing with a person and mirrors and so on, right? So it does something. It's surprising that it works as well as it does, right? And you can play with this also online. I didn't link to it here, but you can find the reference online. And then another clip-enabled thing is something called blended diffusion. And this is a little bit more going into what we're going to talk about in the next couple times, but blended diffusion, this was Avrahani et al. And the location was last year's CVPR. So the idea here is to use CLIP to do image inpainting, right? And this is, again, something that you're probably familiar with a little bit from some of the stuff that's available, where you take a photograph, you remove a region of it, and then you say, I want to fill this in with something that I describe, right? So this used to be like a Photoshop problem where you as a user would make a choice about what to put in, and now you give a description of it and it fills in the space so that the picture image embedding and the text image embedding are closely aligned, right? Only in the inpainting region. And so this is something that now is enabled in stuff like Photoshop Generative Fill just came out with stuff like this. And so this is kind of like I'm not sure there's a direct connection between this and Photoshop, let me just say that. But this is kind of like along the same lines, right? You give a text prompt and it fills in a specific region so that you like it. And then we're going to talk about this a little bit more in future lectures, but the same kind of idea can be used to then kind of like outpaint, right? So the idea would be that you could take a image that's kind of in the middle, and then you could kind of go in one direction is heaven, the other direction is hell, right? With these text prompts that say, kind of continue the image so it's kind of, harmonious with a given text prompt, right? And so we'll talk about outpainting and inpainting a little bit more after we talk about DALL-E. And so again, all this stuff was kind of like enabled by CLIP. And again, CLIP only came out a couple of years ago, right? So, and I think this was another example of a paper that basically was released on arXiv or released as code. People started to use it even before it was actually published anywhere. And then there's already like a zillion CLIP to blank or blank to CLIP papers out there. So again, it's just kind of another element of how fast research moves in this field now. And so, yeah. All right, so questions or comments about what I talked about? So again, homework 3, one of the problems is for you to do something fun with CLIP, right? So now that you've seen this, you know kind of how it might work. I'm curious to see whether you could do something kind of clever with CLIP that kind of is fusing this image and text domain. I mean, it may be hard to come up with something that no one has thought of before, but I'm curious to see just kind of how well it works for playing around. Is that a question? Or, yeah. Question?
So I'm not sure if you have an answer to this.
Okay.
When you're generating images with stable diffusion,
Mm-hmm.
like a heuristic where you would set something called clip skip equal to 2 rather than 1. I'm not sure if you would know that.
I'm just going to write this down for my future reference. Clip skip in stable diffusion? Yeah. I don't know the answer to this. Okay. But we're going to talk about stable diffusion next time. So I will put this on my list of things to look up, right? Or you could look it up too. But yeah, so next time we're going to talk about basically stable diffusion and DALL-E and kind of putting it all together, right? In some sense, that's the lecture. And the following lecture is going to be like extensions of this, all the stuff that you've been hearing about, like control net and stuff like that. We're going to talk about that in the following lecture, right? So that's kind of like, in some sense, the key endpoint I wanted to get to for the class was being able to understand all the cool stuff that's happening with image generation, but to get there, we had to kind of go along the lines of all this language stuff. So I think it was good. So let me stop my recording.